Greetings, I'm Salvador Cordova. Welcome to Lecture 1.3 entitled Physical and Chemical Properties in this college-level general chemistry lecture series presented by the Evidence Reasons Academy. The material covered in this video is almost verbatim from the OpenStax General Chemistry book 2E. And is reproduced here in this video under a Creative Commons License 4.0 as detailed in the video description. Thank you for joining me today. As you can see, I'm using a new headset microphone. It's different than my regular microphone, this Blue Snowball, partly just so that I could have constant volume levels. I don't think the audio quality is quite as good as of this headset with the Blue Snowball, but please feel free to provide feedback in the comment section about whether you feel the audio is adequate. One way to learn or relearn something is to teach it. And learning by teaching is one of the reasons I was motivated to make this series of general chemistry videos. But the other reason I'm creating this video series is to serve our channel's viewers with high quality, free of charge science education. In my opinion, what is offered in these free videos is worth far more than an entire bachelor's degree in certain disciplines at certain universities which charge over a quarter million dollars to get a bachelor's degree in certain so-called social science disciplines of questionable scholarly value. With that, let's dive right into lecture 1.3, Physical and Chemical Properties from OpenStax. Lecture 1.3, Physical and Chemical Properties. By the end of this section, you will be able to identify properties of and changes in matter as physical or chemical, identify properties of matter as extensive or intensive. The characteristics that distinguish one substance from another are called properties. A physical property is a characteristic of matter that is not associated with a change in its chemical composition. Familiar examples of physical properties include density, color, hardness, melting and boiling points, and electrical conductivity. Some physical properties, such as density and color, may be observed without changing the physical state of the matter. Other physical properties, such as the melting temperature of iron or the freezing temperature of water, can only be observed as matter undergoes a physical change. A physical change is a change in the state or properties of matter without any accompanying change in the chemical identities of the substances contained in the matter. Physical changes are observed when wax melts, when sugar dissolves in coffee, and when steam condenses into liquid water. Figure 1.18. And we'll look at that briefly. Other examples of physical changes include magnetizing or demagnetizing metals, as is done with common anti-theft security tags, and grinding solids into powders, which can sometimes yield noticeable changes in color. In each of these examples, there is a change in the physical state, form, or properties of the substance, but no change in its chemical composition. So let's look at figure 1.18. Here's figure 1.18. Panel A, wax undergoes a physical change when solid wax is heated and forms liquid wax. Panel B, steam condensing inside a cooking pot is a physical change as water vapor is changed into liquid water. The change of one type of matter into another type, or the inability to change, is a chemical property. Examples of chemical properties include flammability, toxicity, acidity, and many other types of reactivity. Let me read that again. The change of one type of matter into another type is a chemical property. No, I think there is a problem with the way they stated it. The change of one type of matter into another type is a chemical change, or the ability of one type of matter to change into another type is a chemical property. So I don't think that's worded quite right. Anyway, let's move on. Examples of chemical properties include flammability, toxicity, acidity, and many other types of reactivity. Iron, for example, combines with oxygen in the presence of water to form rust. Chromium does not oxidize, figure 1.19, which we'll cover shortly. Nitroglycerin is very dangerous because it explodes easily. Neon poses almost no hazard because it is very unreactive. And so let's look at figure 1.19. Panel A, one of the chemical properties of iron is that it rusts. Panel B, one of the chemical properties of chromium is that it does not. A chemical change always produces one or more types of matter that differ from the matter present before the change. The formation of rust is a chemical change because rust is a different kind of matter than the iron, oxygen, and water present before the rust formed. The explosion of nitroglycerin is a chemical change because the gases produced are very different kinds of matter from the original substance. Other examples of chemical changes include reactions that are performed in a lab, such as copper reacting with nitric acid, all forms of combustion, burning, and food being cooked, digested, or rotting. So let's look at figure 1.20. Other examples of chemical changes include reactions that are performed in the lab, such as copper reacting with nitric acid, all forms of combustion, burning, and food being cooked, digested, or rotting, figure 1.20. So panel A, copper and nitric acid undergo a chemical change to form copper nitrate and brown gaseous nitrogen dioxide. Wow, interesting. So that's copper and nitric acid undergo a chemical change to form copper nitrate and brown gaseous nitrogen dioxide. Okay, so it looks like in this flask we have copper wires here, and I guess the blue substance is nitric acid, and then we see the brown gas, the gaseous nitrogen dioxide. And then in panel B, during the combustion of a match, cellulose in the match and oxygen from the air undergo a chemical change to form carbon dioxide and water vapor. Panel C, cooking red meat causes a number of chemical changes, including the oxidation of iron in myoglobin that results in the familiar red to brown color change. And panel D, a banana turning brown is a chemical change as new, darker, and less tasty substances form. Properties of matter fall into one of two categories. If the property depends on the amount of matter present, it is an extensive property. The mass and volume of a substance are examples of extensive properties. For instance, a gallon of milk has a larger mass than a cup of milk. the value of an extensive property is directly proportional to the amount of matter in question. If the property of a sample of matter does not depend on the amount of matter present, it is an intensive property. Temperature is an example of an intensive property. If the gallon and cup of milk are each at 20 degrees Celsius, room temperature, when they are combined, the temperature remains at 20 degrees Celsius. As another example, consider the distinct but related properties of heat and temperature. A drop of hot cooking oil spattered on your arm causes brief, minor discomfort, whereas a pot of hot oil yields severe burns. But the drop and the pot of oil are at the same temperature, an intensive property. But the pot clearly contains much more heat, an extensive property. Okay, I need to get on my soapbox a little bit here. I've heard some disturbing things from creationist quarters talking about entropy. Entropy is an extensive property. So a cup of water at standard temperature and pressure has much less entropy than several gallons of water. So when I would ask, what has more entropy, a living human being or a dead rat? The answer is a living human being has more entropy for the simple reason it has more water, because entropy is an extensive property. So if you're a creationist, please don't use the second law of thermodynamics. You're going to get slaughtered because you need to know what entropy is. And if you don't realize it's an extensive property, you're going to be slaughtered. That was a very unfortunate proposition by a number of creationists. Perhaps I should withhold their names, lest I irritate them anymore. But just don't use, just a bit of advice, even though I'm a creationist, please do not use entropy arguments, thermodynamic entropy arguments in defense of God's creation. So, end of sermon. So we have some inserts here that I'll cover briefly. This is just maybe to help you. They have this thing called a hazard diamond. And if you could see my cursor, it's this diamond right here, which is actually made of 4 smaller diamonds. And let me just read this. You may have seen the symbol shown in figure 1.21, and this is figure 1.21 right here, on containers of chemicals in a laboratory or workplace, sometimes called a fire diamond or a hazard diamond. This chemical hazard diamond provides valuable information that briefly summarizes the various dangers to be aware when working with a particular substance. And so figure 1.21 is from the National Fire Protection Agency, NFPA. Hazard diamond summarizes the major hazards of a chemical substance. Now, I should mention this is helpful because if you do work in a lab, you're going to see symbols like this on perhaps some bottles or containers of chemicals, and it's just helpful. So I would presume, I don't know if the colors mean anything. Well, let's just keep reading. Maybe it'll tell us. The National Fire Protection Agency, NFPA 704 Hazard Identification System was developed by NFPA to provide safety information about certain substances. The system details flammability, reactivity, health, and other hazards. Within the overall diamond symbol, the top red diamond specifies the level of fire hazard, temperature range for flash point. So apparently the colors are fixed. That's as far as I know here. Correct me if I'm wrong. The blue left diamond indicates the level of health hazard. The yellow right diamond describes reactivity hazards, such as how readily the substance will undergo detonation or a violent chemical change. The white bottom diamond points out special hazards, such as if it is an oxidizer, which allows the substance to burn in the absence of air/oxygen, undergoes special undergoes an unusual or dangerous reaction with water, is corrosive, acidic, alkaline, or a biological hazard, radioactive, and so on. Each hazard is rated on a scale from 0 to 4, with 0 being no hazard and 4 being extremely hazardous. I'd presume water would be the nicest, one of the nicer. You ought to get zeros for all the hazards. And I don't know how that would be classified for specific hazard. I guess it would be just blank. So that's just something to learn. And there's some specifics here. Perhaps no need to go into the specifics. We'll just move on. While many elements differ dramatically in their chemical and physical properties, some elements have similar properties. For example, many elements conduct heat and electricity well, whereas others are poor conductors. These properties can be used to sort the elements into three classes: metals, elements that conduct well; nonmetals, elements that conduct poorly; and metalloids, elements that have intermediate conductivities. The periodic table is a table of elements that places elements with similar properties close together. Figure 1.22. You will learn more about the periodic table as you continue your study of chemistry. So let's just look briefly at this periodic table. And when they say that they're grouped together, I believe that means the groups in terms of the columns. So we have group 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Group 10 elements are pretty cool. There's a lot of research in nuclear transmutation that involves group 10 elements, and the numbers go all the way to 18. And let me read a little more. Figure 1.22, the periodic table shows how elements may be grouped according to certain similar properties. Note the background color denotes whether the element is a metal, metalloid, or nonmetal, whereas the element symbol color indicates whether it is a solid, liquid, or gas. How about that? I like that. That's a very nice form of the periodic table. I don't remember it being this detailed with the color coding, which is great. I mean, some of the ones that I'd seen. So when they say it's liquid or gas, that is at standard temperatures and pressures. So hydrogen is a nonmetal, and at standard temperatures and pressures, it is a gas. Helium is similar in the sense that it is also a gas and a nonmetal. I will point out, having taken astrophysics, the definition of metal is a little bit looser for in astrophysics. So some things that are listed as nonmetals in a standard periodic table may not be regarded as such when talking about astrophysics. Just a point of something to alert you to. And let's look at standard temperatures and pressures. Bromine and mercury are liquid. And a lot of the other elements are solid. And that's it for lecture 1.3. So again, just to recap, this section should help you identify properties of and changes in matter as physical or chemical, and identify properties of matter as extensive or intensive.